Hi guys, welcome back to Data Every Day. Today we're looking at a data set of New York City Airbnb data, basically about different locations. And we're going to try to predict whether, here if I select all the columns, we can see at the end we have this column availability 365. And so we're going to try to see if we can predict whether a given location will be available 365 days out of the year or not. So it's a binary classification problem that we're going to create the labels from this column here. Alright, let's get started. I have the task for today, which is given data about Airbnb locations in NYC. Let's try to predict whether a given location, I'll say, will be available 365 days out of the year. And we will use a TensorFlow artificial neural network to make our predictions. So let's go ahead and import these libraries I'll be using, which is NumPy, Pandas, matplotlib.pyplot, pill to view an image. The dataset actually comes with a New York City map image, which we can use to see some interesting things. For pre-processing, we're going to use both the min-max scalar and standard scalar for different purposes, and a train test split function from sklearn. We'll also include the class weight from sklearn to allow us to account for the skewed classes, and we'll train our model using TensorFlow. Alright, so let's get started. Let's load in our data using pandas.readcsv. We can grab the CSV file right here, copy the file path, paste it in, and we can take a look. And as you can see, right off the bat, we see we have at least some null values, so that's something we'll have to take into account. We have 16 columns, 15 of which are potential features, but we also notice that there's probably a few columns here that we're not going to need. So let's go ahead and get some info. So this is just going to show us like some basic information and which columns might have some null values. And there's 48,895 examples. So you can see there's a good number of these here that don't have any nulls. That's good to know. Alright, so before we actually get into processing the data, let's take a moment to visualize it a little. So let's plot here. Yeah, I'll just paste it in. I'll paste in these little markdowns. So let's plot all the Airbnb locations on the provided image of NYC. So this is a cool thing. If we open the image using image.open, this is from pill, we'll open this file here, newyorkcity.png, and we're going to store it in img here. Then we can plot it in a figure. Let's give it a fig size of 12 by 12. And we're just going to turn off the axis for the plot. This is just an image. And we're going to use plot.imshow for image show. And we're showing img. And I'm going to include the extent here, which is basically just just the axes, like the min and max of each axis. So on the x, we have 0 and 1 as the min and max, and on y we have 0 and 1 as well. And you'll see why I'm doing that in a moment. Then we'll do plt.show. And we can see we have an image of New York City. The city is actually the dark gray, and the surrounding area is light gray. So what we're going to do is I want to see if we can actually plot the actual Airbnb locations on the map. So we can use the latitude and longitude values to plot points on the map. So let's get this. If we select only, we're gonna slice the data frame, but only get the longitude and latitude columns. So longitude, latitude, and all rows. So that looks like this. I'm going to make a copy of that, and I'm going to store it in chords. Just take a look at chords. Alright, so we have this nice copy of the longitude and latitude, and what we're going to do is use the longitude as the x value and the latitude as the y. However, the reason I use this extent thing is because these are obviously global position coordinates. So they don't mean anything within the context of the map. So what I'm going to do is I'm going to apply min-max scaling. So I'll get this in. Let's apply a min-max scalar transform to these two columns so that we can plot them along the axes. So I'm going to scale each column so that it takes on values between 0 and 1, and that will allow it to match up with the extent that I chose. So we're going to create a min-max scalar. That's going to be the min-max scalar from sklearn, and we're going to chords is going to be min-max scalar.fit transform chords. So it's just going to apply, it's going to scale each column to have values between 0 and 1. And this will return a NumPy array, so I want to keep it as a data frame so we can take another look at it. So I'll keep the columns the way they were. And yeah, we'll take another look at that. So here is the scaled version of this. The relationships between the data points are still the same, but the range of values is different. Alright, so now let's actually let's plot it. So I'm going to take everything we did up here, so not the image open, but all that. I'm going to paste it in here, except the difference is I'm going to plot a scatter plot on top of the image. So the x is going to be chords sub longitude, and the y is chords sub latitude. That's another reason I turned it back into a data frame, so that we can reference it like this in terms of columns. Okay, I'm going to make the size of each dot smaller. I'm going to include a color as well. The hex code is 57DB80. It's a nice light green. And we'll turn down the opacity of each point. And I'll give it a title. So Airbnb locations in NYC. And I actually was messing around with this a little, and the extent is, it's off by a little bit, so I found some better values for it. I'm just going to plug this in. It's very close to 0.01, but it's negative 0.02, 1.045. This is just so that the points line up with the map more nicely. And it's still not perfect, but it'll do. So I'm just plugging those in. Okay, so let's see what that looks like. And you can see it has actually plotted the XY points onto the map, and it looks like it lines up very well with New York City. So it's very interesting to look at. You can see most of them are in Manhattan, and some of them are in Brooklyn, Queens area, but very few in Staten Island, very few out here. But you can see it's very cool that Central Park is completely empty. So yeah, I just thought this was a pretty cool little visualization we could do. And I guess let's move on. So cleaning. Oh, clearning. Hold on. Alright, so yeah, I'll paste it in again. So let's start by removing unnecessary columns and dealing with missing values. So let's look at the unneeded columns first. I'm pretty sure these are the only ones. These first four. I mean, like the name of the host is obviously not going to. It will probably not have so much information about whether or not it's available 365 days out of the year. The name, the name might actually have some information, but for the purposes of the video, I'm not going to go into NLP. Although it's certainly possible. We could represent each word as a vector and then feed that into our model. But we're not going to do that today. So we'll drop these 4 columns. So I'll call it unneeded columns. And it's just going to be a list of these. So let me just go through and process this. Okay. and we're going to drop those. So data.drop unneeded columns, axis 1. Okay, so we dropped them, and now let's take a look at the number of missing values we have. So if we check the data.isNA, that'll just give us true and false values whether or not there's a missing value in that location. So this would be a missing value. You can see it corresponds to this one. Alright, so if we sum across the rows, we'll get the total number of missing values in each column. And if we sum across the columns after that, we'll get the total number of missing values in the whole dataset. So let's print total missing values. Alright, so just good to see that to begin with. Then we will, like I said, if we sum across it, we'll get the total number in each column. But what's a little more useful than that is instead of summing, is we can take the mean, which will give us the percentage of missing values in each column. And so you can see there's 20% missing values in these two columns, but that's all we have. Those are the only missing values we got. So we have to think about this. We have to take a look at the data again and figure out what to do with these. So it's last review and reviews per month. So something I noticed right away is that anytime we have a missing value, we have a 0 in the number of reviews, which makes sense. It's saying if there are no reviews, there's clearly no last review, and there's no reviews per month. Now, I don't want to throw these columns away, but this presents an issue because, okay, one of the ways I could deal with the missing value is by imputing a mean of some sort. And the thing is, I can't take the mean of a date. What I could do is separate it into a year and month column, and then take the means of those. But then we have a problem of there still being no reviews, so it doesn't really make sense to have a last review when there are no reviews. Doesn't really make sense. Reviews per month, on the other hand, this could be encoded as a 0. If we have 0 reviews, we could also we have 0 reviews per month. So I think what we can do is just drop the last review column. I mean, the other option for last review would be to one-hot encode all the dates, but there is a obvious problem with that. If we look at the last review column and look at the unique values in it and count up how many we have, there's 1,765 unique last review values, which is it's a lot of columns to add. That's a lot of columns to add, and for very little useful information. So we're just going to drop it. We're going to drop the last review column, and then we're going to keep this column, but change the null values to be 0, so that it matches up with this. Alright, so I'll mark it down here. Because the missing values in the last review column are difficult to deal with, we will drop that column and fill the NaN values in reviews per month with zeros, since a missing value implies there are no reviews for the location. So data equals data.drop last review, and we're dropping from the column axis, axis 1, and then data sub reviews reviews per month. Let's just copy that. It's going to be filled, so fill NA, which will fill null values with value, with 0. So we're filling all the null values with 0 in this one, and we're dropping the last review column. Okay, now that's done, let's print the total number of missing values again. And you can see we now have 0 missing values. Okay, so we're done, pretty much done cleaning the dataset. So let's go on to creating labels. Let's take another look at our data. Actually, let me explain what we're doing. Okay, we want to predict if a location will be available 365 days of the year. So let's change the availability 365 column to be a simple binary column where 1 denotes 365 availability and 0 denotes otherwise. So here's our new data set. It's nice and clean now. And we have this column that we want to turn into a label column. So we can do this by grabbing the column name and saying data sub availability 365 dot apply. This will apply a function to each element in availability 365. So we'll apply a lambda function that takes in some x, which will be a given one of these, and it will return 1 if x equals 365, and otherwise it will be 0. So anything that isn't 365 available will be encoded as a 0, and anything that is 365 available will be encoded as a 1. And so that's going to be the new column. And let's check the class distribution for this new column. So we want to know how many of them are 365 available. So we can get this by, let me paste this in. So we can get the value counts of this column. And that's going to give us the number of values in each class. And we could divide it by the length of the column to get the percentage, like the class distribution in percentages. So 97% of the data is not 365 available, and only 2.6% is. So we can see from the class distribution that we are dealing with severely skewed classes. 365 availability only occurs in 2.6485% of the data. So we do have classes now. So let's move on to encoding features so that everything is represented in a numerical form. Okay, let's get a list of the unique values, for each categorical feature, so we can decide on how to encode them. So these are the categorical features. So let's say, okay, let's take another look at the data. We now have this zeros and ones here. If I get a dictionary, that's going to map a feature to a list of the unique values in that feature. So data subfeature.unique turned into a list for every feature in data.columns, but only if the data type of the feature is an object or a string. So you can see this will only give us data values for the categorical features. It's going to ignore latitude, longitude, price, and all the rest. So just neighborhood group, neighborhood, and room type. So right, so we want to know how to encode these. And we can see neighborhood group is a nominal feature because there's no ordering between the values. Neighborhood is also a nominal feature, has a whole bunch of values, and there's no ordering between them. And room type is also a nominal feature because there's 3 values and no ordering between them. So, I mean, technically we could encode this as an ordinal feature if it wouldn't really be good, but you could say private room is 0, shared room is 1, entire home/apartment is 2, because it's sort of about size. But like, how do you say shared room is bigger than private room, or vice versa? Not clear, so we'll keep it as nominal. So it appears that all 3, whoops, just reset. Okay, it appears that all 3 categorical features are nominal, no ordering, so we will perform one-hot encoding on them. So let's make a function called one-hot encode. It's going to take in a data frame, a list of columns, and a list of prefixes. We'll start by creating a copy of our data frame. And then for each column prefix pair in the zip of columns and prefixes, so zip will just pair up the values of columns and prefixes element-wise into tuples, and then we can index them 2 at a time as column and prefix. We're going to start by making a dummies data frame using pandas.getDummies. It's going to get the dummies for the given column and including the prefix. So that will be the one-hot columns. And then we can concatenate using pandas.concat the original data frame and the new dummies columns next to each other. And then store that in the new df, and df is we're going to drop the original column from which we created the dummies. This is no longer needed. Then we'll return df, and there's our function. So let's apply this to the dataset. Data equals one-hot encode. So we'll pass in data. We'll pass in a list of columns, which will be, in this case, alright, so it's neighborhood group, neighborhood, and room type. Alright, then we'll also have a list of prefixes, which we can decide. How about G for group, N for neighborhood, and R for room type. So if we take a look at it, you can see we now have fully numerical data with all these different one-hot columns at the end. So we now have 237 columns, and everything is numerical form. So let us start. Yeah, I'll just copy and paste. Splitting and scaling. So our data is now in fully numeric form, so let's scale the data so that each column has mean 0 and unit variance. So first we need to split the data into x and y, so our features and our target. So y is going to be just the availability 365 column. That's what we're trying to predict. And we'll just make a copy of it. And then x is going to be everything except the availability 365 column. So we're dropping it from axis 1. And we'll make a copy of that as well. Alright, then we'll create a standard scalar. So this is a scalar from sklearn that gives each column of the data frame mean 0 and unit variance. And so x is going to be scalar.fit transform x, but we can turn this back into a data frame so we can see it. So we'll keep the columns the way they were, x.columns, and we can take a look at it. You can see this is the same as this, but all the columns have been scaled so that most of their values lie between -1 and 1. Okay. So now that the data has been now that the data has been scaled, we only need to split it into train and test sets. So we can just use the train test split function from sklearn to do this. Xtrain, xtest, ytrain, ytest equals train test split xy with a train size of 70%, and we'll include a random state of 200. This is just so that we can reproduce the split, and this also shuffles the data for us. So now we have 4 different sets of data, and we can begin modeling. So since we're dealing with tabular data, we will use a simple 2-hidden layer neural network. So no need to do anything fancy. X.shape, we can get the number of features here. There's 236 features in a given example. So let's start building our model. We'll have the input layer be a tf.keras.input, and the shape is going to be a vector of length x.shape sub 1. So that's going to be this value. So each vector we're feeding in is going to have 236 features. Let's also give this a name. How about input layer? Alright, then we'll create two hidden layers, a hidden 1 and hidden 2, and they're going to be the same, tf.keras.layers.dense, so they're both dense layers with 64 activations and an activation function of ReLU. Let's also give them some names. Hidden, this one will be 1, this will be 2. And here we can pass in inputs to the first one and pass in hidden 1 to the second one. Alright, then our output layer will be also a dense layer, but it's only going to have one activation. This will be the probability estimate for, basically it's the probability that the example is 365 days available. So that's going to have a sigmoid activation so that we get values between 0 and 1 for a probability. And we'll give this a name, output layer. We can pass in hidden 2 to this one. And we can create our model, which model will be tf.keras.model. We just have to pass in the inputs and the outputs. Alright. So let's generate a summary and graphical representation of the model for better understanding. So I'll print out model.summary. This will give us information about the parameters, and then we can also plot it using tf.keras.utils.plotModel model. And so here's the summary. You can see we have 19,000 parameters that we can tune, well, that the model will tune. And here is a small graphical depiction of what the model's doing. So we have the input, feeds it through the first dense layer, then to the next dense layer, and then to the output, which is just a single value. So we can begin training. So let us compute some class weights before fitting the model, since our classes were so skewed. Say are so skewed. So I'm going to, at the top, I imported class weight from sklearn.utils. So we're going to use the class weight dot compute class weight function, and this is going to compute. It's going to get the class weights for the classes. All we have to do is pass in the mode, which will be balanced. So this will try to balance the classes. This will allow the loss function to penalize more heavily for the underrepresented class. So we're passing in all the unique values in our classes. So this is like the labels here, just 0 and 1. And then we actually pass in the train set labels that we want to apply the class weights for, that we want to calculate them for. That should be compute. Alright, so TensorFlow needs this to be in a dictionary form, so let's enumerate it. Enumerate, and let's turn that into a dict. So I'll just indent. Alright, and we'll call this class weight. Okay. So we can take a look at them. I'll just hide this output from the notebook. And you can see the class 0, because it has so many more examples, has been not penalized much less heavily, so 0.5, and the class 1 is penalized much more for getting it wrong, so 19 times more. So let's start training. We'll create a batch size. How about 32? And we can train for 60 epochs, worked for me. Then we can compile the model using an atom optimizer, binary cross entropy loss, and for metrics, we'll use 2. We'll use accuracy, but because we have such skewed classes, accuracy is not enough. We should also have something that is more, it's better at representing performance within classes. So we'll use the area under the rock curve. So name equals AUC. So let's store the model's fit history in history. It says history, hold on. Okay. So we'll train the model on xtrain, ytrain. We'll give it a validation split of 20%. Let's also specify the class weights that we computed, and then include the batch size and epochs. And we'll also include a callback function that will just allow our model to converge more easily, which will be tf.keras.callbacks.reduce learning rate on plateau. Okay, let's train the model. Now I'll go for 60 epochs. In the meantime, we can plot a graph of the model's performance over time. So we'll create a new figure with matplotlib, pyplot, figure, fig size equals 20 by 5. I want a wide graph here. And I'm going to include two subplots. So subplot in a 1 by 2 grid, and this is subplot 1, and then subplot 2. Alright, we also want to include the axes. So we're going to have the x-axis, let's call it epoch range. It's just going to be a range of the epochs. And we're also going to have 4 different things for plotting on the y-axis. So it will be train loss and val loss. And I'm just going to define them together. History.history sub loss and history.history sub val loss. And we're going to do the same thing but for the AUC values. So I'm just going to run through here and grab these. That's AUC. And then on the first subplot, we're going to plot the loss. So, is this finished? Okay, I'm just going to paste them in because it's just a lot of typing. But basically, we're just plotting the epochs range against the train loss. That will be the training loss over time. And then the epochs range against the validation loss will be the validation loss over time. Alright, and then for the second subplot, I'm just going to do exactly the same thing, but for the AUC. So that's AUC over time. And we can show the results. Epochs range not defined. Oh, epochs range. Alright, and you can see the loss has converged, and the AUC, it looks like the AUC actually might be too low here. Like it looks like it was higher up here. So you might want to consider retraining for like 20 something epochs. In any case, let us see the model's performance. Results. So we'll store the results in model.evaluate. We're going to evaluate on the test set, xtest, ytest. I'm just going to turn verbose mode off. And we're going to print the accuracy, which will be results sub 1, because results sub 0 is the loss, and the rock AUC is going to be results sub 2. And you can see we have an accuracy of about 84% and an AUC of 0.7. So it's not great. There's one thing I'd like to try is let's try retraining for a smaller number of epochs. So if I can actually get the maximum value of the AUC by using numpy.argmax of val AUC. So epoch 28 is it seems like right here. And that was actually, because it starts at 0, we will train for 29 epochs. So I want to see if this gives us better results. I'll redefine the model, reset the weights, then recompile and fit. And this will only train for 29 epochs. So Just give that a second. I'll pause the video and restart when it's done. Alright, it's almost done. And let's take a look. So, alright, it looks like it's converged in a better fashion. Let us see the results. Alright, so not fantastic. Let's take a look. So let's take a look at this. So ytest is the actual values of our labels. We can call model.predict on xtest to get predicted values for our labels. So right, so these are actually probabilities. So what I'm going to do is first I'm going to squeeze it, which will just remove the extra axis, and then I'm going to check if it's greater than 0.5. So this is true, false, and then I'm going to turn that into integers to get something very similar to ytest. So we can compare these now. So ytest equals to get the whether our predictions were correct or not. So if we get the sum of that, numpy.sum, this is the total number of correct predictions. If we get the mean of that, that will be the accuracy, right? Okay, but now let's see. So I want... Okay, so this is just the accuracy. I want to find a way to know how many of the positive examples we got right. So ytest looks like this. If we do ytest equals 1, this is not as easy as I thought. I'll have to consider this. I want to know how well do we do at predicting the 365 examples. So give me 1 second. Alright, I figured it out. So we're going to create something called yPrediction. So we're going to predict the xtest values again. And again, we're going to squeeze it to remove the extra dimension. And we're going to check if it's greater than 0.5. So this will be it will be true if it's a 1 and false if it's not. So if we turn this into an integer values, this is very similar to our ytest. So ytest is a pandas series. Okay, so what we'll do is we will try to make these identical. So let's turn this into a pandas series. Looks like the very same thing. Let's call this ypredictions. And then let's call ytrue. Alright, so ytest just looks like this, but the indices don't match up. So this goes from 0 to 14,000 something. This is all scrambled around because we shuffled the data. So let's call a reset index on it. Include drop equals true, so it doesn't add the old indices as a column. That will look like this, which is the same format with the same indices as ypred. So let's call this ytrue. Okay, so now we have yPrediction and ytrue, and because of this, we can now see only how we did in the positive class. So ytrue equals 1. This is going to be the indices. So if I get the index of that, dot index, this will be, that's not actually doing it. I have to evaluate it at ytrue. So ytrue, hold on. I'm going to use this as the index in ytrue. So ytrue sub this will give us all ones. So this is just the indices here where it's equal to true. So dot index there. We now get the total. These are the indices in which we just had positive examples. And so what we can do now is ypred. So I'll call this positive indices. Positive. YPred evaluated at positive indices. Okay. Equals Y true. I'll do it the other way. This will be YPred, this will be Y true. So this is going to see how many of the positive ones did we get right. So if I take the mean of this, numpy.mean, we get 62%. Okay, that took too long. Well, we got 62% of the positive examples correct, which is fairly good, considering there are only 2.6% of them or something. All right, that will conclude today's video. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.